Hello, today we're going to look at the hand warmer design lab. This is a calorimetry experiment, goes well with Unit 6. There are a couple different ways that you could do a calorimetry experiment with AP chemistry, and this is one of them that involves just a little bit more of the inquiry process, where students have to look at a number of different criteria to evaluate the effectiveness of different substances for their use in hand warmers. So you could be, obviously it needs to release heat. It really needs to release an appropriate amount of heat so you don't have safety issues. The substances should be environmentally friendly if they are disposed of improperly, and you have to consider cost as well. Now, you could do all or only some of those parts to have an effective version of this lab. I also wanted to show you two different types of equipment here. I have an actual styrofoam calorimeter thing that I've put a beaker, it just has deionized water, 100 milliliters of deionized water, nestled inside here, and it has the lid. You could also just use styrofoam cups though, and I went ahead and cut out little tops for it, but you don't even need that, and you still get an okay result. And at least if you're doing a comparative study, it gives decent enough results. So you don't have to use anything super fancy, but students definitely need to know about procedures for calorimetry and the sources of error for calorimetry, and how to calculate using Q equals MC delta T, how to identify endothermic and exothermic reactions. So heat of solution is one way that you could do this. You could also do like a heat of reaction. A good one is like hydrochloric acid reacting with sodium hydroxide. That's exothermic. You can measure the temperature change and then find the kilojoules per mole release for the heat of reaction. But heat of solution is what we're going to do today, and I'm going to use two different substances. Typically, I'll give my students 5 or 6 options, or I'll give one to each group, and then they can decide as a whole class based on the results. But the ones I'm going to show you guys today are calcium chloride and then sodium acetate. And I have 1 gram of each of those, and then 100 milliliters of water. Another aspect of inquiry here is you could have students design the the amounts and the amount of water. So it really just depends on how deep you want to go into this with your students. All right, so let's look at the results of this experiment. I just did 2 calcium chloride and sodium acetate. I wound up using 3 grams of the substance in 100 grams or 100 milliliters of water. So to find our overall results in terms of heat of solution, we want to change grams to moles. So I used the molar mass for both of those, got the moles of the substance dissolving. And then we're going to use our Q equals MC delta T for calorimetry experiments. This is the equation. Now typically when we're making a solution like this, or in a reaction where you're combining the two things together, you want to use the mass, the total mass, so the mass of the solution. Now, I don't know what the specific heat of the solution is, so I'm going to assume that it's the same as the water. Usually in questions on the AP exam like this, they will be very, very clear, the heat capacity or the specific heat capacity of the combined solution is blank. And it's usually pretty close to pure water because they're water-based. But so I've seen 4.2. I've seen other ones as well, but that's why I'm okay with estimating that it's the same as water, and I explain that to my students. It might not be, but we don't know exactly, so we're going to just estimate. And then this last part is our change in temperature. So the calcium chloride went up in temperature by 3.6 degrees Celsius, and the sodium acetate went down in temperature by 0.4 degrees Celsius. So that's where I've got, when I multiply, I got the joules released for calcium chloride and then the joules absorbed for the sodium acetate. I always like to tell students to think about the thermometer. If the thermometer is picking up an increase in temperature, that means heat must be going to the thermometer for it to read that change. Same thing if the thermometer is reading a decrease in temperature, heat must be leaving where the thermometer is and going into the system. So the calcium chloride was exothermic when it dissolved, and the sodium acetate was endothermic when it dissolved. Now, to go ahead and find the heat of solution, I changed the joules to kilojoules and divided by the moles of the substance that dissolved. And then at the very end, I always assign the sign. So again, because this is exothermic, it gets a negative value. Endothermic gets a positive value. So that's why I like to do that at the very, very end. Q, I will usually have them just use the terms released and absorbed, whereas heat of solution, any kind of enthalpy, will use the sign, positive and negative signs. So I picked these two examples on purpose because I knew one was exothermic and one was endothermic. Obviously, the exothermic one is going to be the better hand warmer of the two. But in the lab, I'll usually use a couple different substances that are exothermic and maybe one or two that are endothermic. And then they can pretty easily and quickly eliminate the endothermic ones. They will not make good hand warmers. And then they'll have to look at the amount of heat released. They'll have to look up the cost. I'll usually give them a website to use and tell them, okay, like cost per 500 grams or something like that. And then I have them look at the safety data sheets for the different substances to see if there's any that are like majorly egregious in terms of their disposal or their toxicity or something like that. And then they can have a little debate if you want them to on which one's the best and why. And I always tell them that you don't have to necessarily agree with your team members. But yeah, there's a lot of ways that you can extend upon this kind of basic experiment. Of course, you really want to talk about the most important source of error, which is heat loss to the calorimeter itself or to the surroundings. So especially when you have an exothermic process like this, when it is dissolving and releasing heat, some of that heat will get into the calorimeter itself. So the beaker, if you use the big calorimeter with a beaker inside, the glass can absorb some of that, the styrofoam can absorb some of that, the air surrounding it can absorb some of that. So that means that your thermometer will pick up less of a change in temperature than I really should have. So this number probably would have been bigger if it was a perfectly insulated scenario.